Okay, so then the next task that we'll discuss is the performance simulations. And the goal of this is to really understand the broad performance at a more general level of this plug-and-play system. And then to also test the design methodology. So whatever design methodology we come up with, we want to be sure that it will apply to, whatever subset of homes we think it applies to. And so in order to test that, we will basically be putting in virtual duct systems into different simulations, running those simulations, and confirming that that design provides the comfort that we expect. So to execute this task, what we're doing is we've created this very detailed multi-zone energy plus model. And we've started with the Pittsburgh lab home as a geometry. And then we've added these detailed airflow networks and a thermostat control. The airflow network basically is a model of the duct system, registers, return plenum, and all of the different airflows throughout the house. So we've got a very detailed understanding. If you have the fan turn on and it pressurizes the duct system, we can now predict where the air is moving throughout the house. So then, now that we have this baseline model, our next step is to verify that that model is accurate. And so we're comparing measured data to the simulation. We'll see a little bit of that on the next slide. But we really want to make sure that this model is realistic. We're not getting too much into calibration. We don't want to over-calibrate the model, but again, we want to make sure it's realistic.
Can you remind people who may not be familiar, we've got some new contacts on the phone today. The lab home in Pittsburgh, I know, is near zero energy, but can you remind anybody of any of the specs for the performance level of that house?
Yeah. So the lab house is it was built a few years ago as part of a Building America project to test out different air delivery systems. It's a highly insulated house, highly air sealed house. The blower door number runs around 0.6 to 0.7 ACH 50, and we're talking about extremely low loads. This is a roughly 2,500 square foot home. And the total thermal load is about 16,000 BTUH, so a little bit over a ton, about a ton and a half, and that's the total heating load, and then the cooling load is even lower than that. So we are talking about a highly insulated house on the level similar to a passive house. So this is a little bit beyond maybe your typical zero energy ready home. But represents a good test bed for a very energy efficient home.
Okay, thanks.
So just briefly, I wanted to touch on some of the things we're looking at with these performance simulations. The bottom chart here shows the supply air temperature, and it's the difference between the measured data and the model. So whenever we see zero, that means that the difference is zero and the model is dead on. And we see a little bit of a range here, but we're talking about the difference of a few degrees. So the model is very accurate at predicting the temperature drop along the length of the ductwork. That's critical in understanding the energy that's delivered to the zone and ensuring that we're getting an accurate, realistic model. The top graph then shows a comparison, a similar model versus measured comparison, this time for the actual zone air temperature, which has many more factors influencing it, but ultimately that's what we want to be dead on with the model. We want to make sure that, we built this whole virtual house, virtual ductwork, all of this, we want to make sure that it's predicting the rooms are at the temperature that we actually saw in the real world. That's critical because we're trying to use this model to understand comfort, and our key metric for comfort is temperature. And so you can see here that the rooms, some of the rooms are closer than others. This is kind of in the middle of the adjustment phase, so we're still in the process of making some tweaks to improve that accuracy. but it's coming along quite well.
So I wanted to make a point with the performance simulations task is that there's a lot of things at play here. We've got some really advanced techniques being developed and utilized to allow this modeling to proceed and make these comparisons. But we're utilizing information, again, fed from our lab testing for the effective U values of insulated and uninsulated ductwork because we've tested both at the lab house. We are feeding forward from the lab testing into the performance simulations the pressure and airflow relationships, and we're also bringing in the real world measured data from the lab house. So this speaks to the nonlinearity, but the heavy degree of interrelationships we have between our tasks. And so the performance modeling environment is really critical to the success of our project because it allows us to really pool a lot of these things together. Show that we can basically closely match the conditions that we've measured, and then we can start to predict forward and expand our application and project how the plug-and-play system will perform in other climates and other size homes under a variety of conditions.
Yeah, we've built a framework here using the Pittsburgh Lab House that will let us very easily swap in a new house floor plan, a new geometry, or a new duct layout. So we can swap in more of a traditional duct layout, or when we're testing the plug-and-play system, we can add a duct here, remove a duct there, and see the impact that that has on comfort. So that as we're finalizing the design methodology, there's going to be a lot of interplay with the model where we're verifying that that design methodology is going to ensure comfort in the home. So on to the next task, which is field data collection. And we've talked about this somewhat, but what we're doing is up at the Pittsburgh Lab House, which again is this highly insulated, basically passive house level of insulation home, we've installed this plug-and-play system. So what we want to do with this now is measure the seasonal comfort performance and then use this really as a test bed to understand any changes that might need to be made in the real world. So the first duct system that was installed was kind of based on our experience, what we thought would be appropriate in this house. And once we finalize the design methodology, we'll be able to modify that duct system using the design methodology and actually test it as a real-world example of the performance of this system, as a real-world example to understand the comfort that the system may provide, and just kind of as a way to get our hands dirty, to understand any shortcomings that we didn't anticipate in previous research or that a model perhaps doesn't fully capture.
Before you go further, we have a few questions in here in the queue that we'll get to during Q&A. Can you go back to the task 4 performance simulation slide for a second? Okay. There's a question here, are we incorporating any smart monitoring associated with the system performance? Example, dual zone. And I think there's whoever, oh, no wait, I'm sorry, that was a separate question. And related to a separate thing. It ran into another one, sorry about that, but answer it anyway.
Yeah, so what we are simulating is exactly what's installed up at the lab house today, and that is a single zone variable capacity furnace. In the bottom left of the slide, you'll see a rendering. It's somewhat small, but it actually shows the physical duct layout, kind of in an X-ray view of the house. So to that extent, yes, it is single zone at this point. We're really just trying to confirm that the model is accurately capturing the detail, the different transient phenomena that is happening in the real world up at the lab house.
Yeah, the modeling environment will give us the opportunity to, a bit later, involve other temperature control strategies, perhaps zone by zone, and things along those lines, other system types. So we'll have the ability to extrapolate and use the power of the simulation engine for a more extensive interpretation of this system.
Okay. So back to the field data. One of the most important things for this system, in order for it to succeed, is that the total pressure can't be too excessive. You know, one of the initial kind of gut concerns that you might have about this type of system is that, you know, wow, these are really small ducts. It's kind of like blowing into a pack of straws or something, that the static pressure might go through the roof. And what we've found, you know, now that we've actually installed the system and we've been testing it, we found that the static pressure isn't actually particularly excessive. Because we've shortened the total duct length, you know, the system is going to be installed centrally in a home. So we're not talking about a 50-foot long duct run, you know, to the other end of the house. It's all short, compact, and central. And then also because it's this smooth walled with these smooth elbows and transitions, the total static pressure has actually been, you know, maintained at a pretty reasonable level. If you look at the chart here, we have some measured data and then a interpretation line, or an interpolation line. We see that the static pressure, even, you know, when we're talking about 300 CFM, is only about 0.35 inches of water. So in general, this is under ½ an inch of water, which is much more reasonable for a typical system, and isn't, you know, extraordinarily excessive, you know, like an inch of water or something. We expect this system to operate somewhere on the range of 200 to 300 CFM. So in that range, we're talking 0.2 to, you know, 0.3, a little bit over 0.3 inches of water, which is very reasonable for existing blower motors that are on the market today.
We're using 2-inch ductwork at
Yeah.
the lab house, which is actually at the smaller end of our spectrum of what we're evaluating.
Yeah, we started with the 2-inch ductwork kind of as the one extreme. And, you know, it's one of the things, like if it works with 2-inch, then it's going to be even better with slightly larger duct runouts. So one of the interesting things that we observed is actually the temperature drop along the length of the duct. And this wasn't something that we had anticipated would be quite as severe as it was. But what we actually decided to do was install some insulation on one of the duct runs. And you see on this chart here that the two supply air temperatures were very similar. We added the insulation, and of course the supply air temperature went up in that bedroom too. And so that's been a very valuable lesson. And you know, one of the things that's going to be critical in ensuring comfort is delivering air at the temperature that you need. And that will also help prevent the air from feeling drafty or anything like that. So these kinds of measurements and observations are influencing our decisions with the design methodology and with the duct material. We'll get into some of that in a little more detail later. And we are actually measuring data in both the heating and cooling season. You know, the climate is Pittsburgh, generally considered more of a heating season, but the cooling season data is very valuable as well. So then a lot of the work that we're doing is really boiling into this design methodology. That's the kind of chief usable deliverable out of this work. And our goal is to create a methodology for designing the duct system. This should be a very simple, straightforward, intuitive approach that really leaves little to no room for error. And the goal is to basically have that methodology, that workflow that, you know, any HVAC technician could pick up in the field and very quickly create a design and then install that system. So the way that we're envisioning this design methodology will work is that you would basically do your typical manual J types of calculations to understand the loads in the house. That would give you the required CFM to satisfy the load for each zone. And then on this little chart here, we're showing just an example of a couple different rooms and the possible output from some different design methodologies. So the way we're approaching this is to think that each of the duct runs gives equal or very similar airflow. So the most simple design methodology would be assuming that each run is giving equal airflow, and you'd simply divide the needed airflow by that nominal amount. Let's say 20 CFM per duct run, and that would give you the number of runs you need to that zone. Now we know as we increase the length or decrease the length of the runs, that the airflow will be impacted. So another approach might be to use a simple multiplier. You know, if your duct run is longer than, say, 25 feet, you multiply it by, you know, some percentage, say 70%. Or if the duct run is very short, it's going to get more airflow, and so you could use a different multiplier. And that would give a much more accurate representation of the design system and should provide a better comfort in the home. So we're exploring some of these different methodologies, and we'll be testing them in the performance simulation. And just one more little bit of data that we wanted to show you was a comparison between our measured data for the pressure drop along the length of the duct, how that relates to the total airflow, and then what we did was compare that to kind of the fundamentals of fluid dynamics. So there's equations that you can use to predict airflow based on the parameters of your duct, and our measured data is those red X's, and it aligns very, very well with kind of the established body of knowledge, which gives us confidence that we'll be able to create this very predictable design methodology.
So I wanted to return for just a moment to our task diagram and give an illustration of a recent milestone point we had this spring in the project, and just sort of the relative progress that we feel we've made in each of the various tasks. And so you'll see that, you know, some tasks have more, some have a little less, but the fact that they all are interrelated, you know, we need to finish up certain tasks to a higher degree, so then we can feed forward into other tasks such as the design method. So we've got a real iterative process here, but it's really helpful. It's really an interesting process for us. We're learning a lot along the way, and we're getting, I think, very good results by addressing all of these tasks basically simultaneously. So we are accomplishing the objectives that we mentioned by completing these tasks in this fashion. And this is going to help us secure partners for commercialization.
So related to that, in looking at some of the questions that are coming in, I think I can actually answer the first one that's coming in. But someone said we're probably addressing this through time and motion studies, traditional versus plug and play. And it was asked what kind of efficiency was seen with the innovative method. I believe based on what everybody's saying, you know, the mock-up is built in our building at this point, but the time and motion studies are a task to still be completed, and the guys can probably comment on the timing of that. But certainly we will be looking at, in that time and motion study, actually getting the feedback just to see what the time is and what we observe from the installation process, how that goes, and then also engaging the people who are doing the installations to get direct feedback from them on what the process was like, how easy it was for them to adapt to using materials in that fashion as well. And then also part of that question was that this person was trying to anticipate the cycle time benefit of the new versus traditional method. We think that there is definitely a cycle time benefit to it. That's one of the main other great byproducts of doing this, in addition to still being able to get the energy efficiency that you're targeting without sacrificing the comfort. One of the other byproducts should be that the cycle time is much faster, that there's less risk with the installations, fewer comfort issues, so it should cost less, be done more quickly, more easy to be done in conditioned space. All of those benefits should come along with the performance benefit, which, you know, being a non-technical person but a more business-focused person, I think would make this a no-brainer if you can get it to work on that level. And then to the last point this person made was, you know, what's the learning curve for trades, adoption by the municipalities, testers? That's part of the evolution process of introducing it to market, and certainly the guys will touch on those as issues. But to circle back, as far as the time and motion studies go, so I can give you guys the direct question there instead of answering somebody's questions, when do you guys think that's going to take place?
Well, we're making good progress on the design methodology. And again, there's several interrelated steps, but this summer we'll be looking at the time and motion studies in our mock-up area.
Okay. Then can you scroll back to, this is the rest of that task 4 slide related question. It just happened to get, we got a little disconnected in that coming in through, yeah, that's the one. So let's see. They said some of the big deltas look pretty big, greater than 5F, whatever that means as a non-technical person.
Degrees.
Thank you. Thank you, Tim. Can you explain the big deltas?
Yeah, so actually some of the extreme peaks that you're seeing in the supply air temperature is just related to the way we were feeding in the measured data into the model. So what we were basically doing is taking the measurement at the supply plenum, so right after the furnace coil, we were taking that measurement and feeding it into the model so that we were just looking at the temperature drop along the length of the duct runout. And there is that kind of period where you get some of these blips, and that was simply related to the way that measurement was taken and being fed in here. The period of interest is really a much smaller region relative to what we're looking at in the graph. Then if we look at the zone temperatures, we see that there is a pretty big spike like in that bedroom 4. And so this was an earlier graph, and what that led us to do is actually change some of the window properties, some of the shading to be a little bit more realistic. And so that spike is in the afternoon. Once we dialed back the windows a little bit, we saw a much closer alignment. So kind of these visualizations are a great tool for us to understand when and where some of these issues might be happening so that we can make changes to the model and really dial in that accuracy.
So we've gone through a tuning process, and I mean, what we're showing here is actually part of that process to calibrate the model.